To explain why boats have stability, we have to bring in some new terms. Weight stability and form or shape stability. This is an empty pipe floating in the water. The G is in the center of the pipe. It has no weight stability. There's no defined up or down on this pipe, and it doesn't matter which side is up. If we turn it around 90 degrees, it will still be in an equilibrium. It won't rotate back. Let's say that we put in some concrete ballast in this pipe. That means that the center of gravity shifts towards the side where the ballast is. And the weight distribution makes sure that this pipe gets weight stability. This again means that the pipe has a defined up or down. Whichever side the ballast is in will be floating downwards, and it will resist heeling moments, as we can see. We heel it, but it will rotate back towards the equilibrium state. So weight stability is how the distribution of weight and the center of gravity G gives the vessel stability. Shape stability or form stability depends on the shape of the part of the hull that is submerged in water. And if this shape changes when the vessel heels over, it can contribute to righting the hull up again towards the equilibrium. We'll have a look here. The pipe, if we rotate it around, there's the shape of the part that's submerged in water doesn't change at all. No change in the shape of the underwater hull means no shape stability. We have an empty milk crate, which is square, as we can see. If we rotate that, we see that the shape of the underwater hull changes, and as we will see, this gives the hull shape stability and makes it upright again. So there's two factors that contribute to a ship stability. One is the distribution of weights on board, which is the weight stability, and two is the shape of the underwater hull, which gives us form stability, shape stability. So we can see if we release it, it will rotate back to the equilibrium position. So G is the center of gravity, and in a square box like this it's easy to find it. B, center of buoyancy. That is the center in the part of the hull that at any given moment is submerged in the water. Now G pushes down, B pushes up, and these two forces are the same size but have opposite direction. G pushing downwards, B pushing upwards, and this is known as the law of Archimedes. Now, if the ship heels over, then B will move. We can see here we heel it over. This means that we lose buoyancy in this volume here, and we get buoyancy in the green volume here. This again means that the center in the volume that's submerged shifts towards the low side. So G is pushing downwards, B is pushing upwards, and we can see there is a distance between these two forces and arm. Moment, torque, equals force by arm. And this pushes the vessel back to the upright position. And how much the center of buoyancy moves sideways when the boat heels over is vital for how much shape stability the hull has. Summarizing, K is the keel, B center of buoyancy, G center of gravity. When the boat heels over, B moves over to the side. B pushing upwards, G pushing downwards. Now the intersection between the vertical line going upwards through B and the center line of the vessel is called the metacenter, abbreviated M. Metacenter M. Between B and M we will find the point Z, in the same height as G, as illustrated on the figure here. The distance GM, metacentric height, is vital for the stability, especially with small healing angles. Whereas the distance GZ, the righting arm, is vital for the stability at larger healing angles, and we will get back to this one later. The distance km from the keel to the metacenter varies with the draft of the vessel and can be taken out from the stability data for the vessel. And the vessel km, as we can see, equals the distance kg and the distance gm. And this formula is vital. If we know two of those, we can always calculate the third one. So km equals kg plus gm. And the bigger GM is, the more ability the vessel has to withstand a healing moment. Positive stability is whenever G is underneath M. When G is underneath M, when the vessel heels over, there will be a righting moment that will try to get the boat upright again, as we see on the figure. Two forces, opposite directions, they're not working in the same point, leads to there being a righting moment that will try to get the boat upright again. And the bigger the distance between G and M is, the bigger the righting moment will be. Neutral stability means that G and M are at the same vertical level. There's no GM arm. So we see the two forces working in the same point, which again means that there is no righting moment. And if a vessel is subjected to a healing moment, then there will be no righting moment to withstand this. Doesn't necessarily mean that it will capsize, but it does mean that it will heel over to a certain healing angle. Negative stability means that G is over M. Then the healing moment will always be bigger than the righting moment and the boat will capsize. We will see in the figure here that G moves more to the side than B does. So the healing moment will continue to heel the boat over. And that doesn't end well at all. GM. The shape stability depends on the hull shape, and there's not all that much we can do about that, even though it changes with the draft and freeboard. The hull shape depends how high up the metacenter M is, and we can say that the wider the width of the boat increases means that M goes higher up. The weight stability depends on the vertical center of gravity, and we can influence the center of gravity by how we distribute weights on board. If we put weights at the bottom of the boat, low down in the boat with a low center of gravity, it means that the distance kg, the VCG, is smaller, hence the distance GM will be bigger. The distance from G to M, that's the metacentric height GM, and it says something about the ability of a vessel to withstand healing moment. And the bigger the GM is, the bigger the ability of the vessel to withstand healing moment is. There are stability requirements for the minimum permissible GM. For cargo ships, this is 0.15 meters. To find the GM, we need to know the kg, VCG, and the km. Km can be found in the stability data for the vessel and depends on the draft. The kg we can calculate. And the connection between kg and m is as follows: km equals kg plus gm. So km equals kg plus gm. Some examples, and this is a formula that we can turn around. Km equals kg plus gm is the same as GM equals KM minus KG, which is again is the same as KG equals KM minus GM. Example, we have calculated that the kg is 3.56 meters. In the stability data for the vessel, we will find that the km is 4.02 meters. We want to find gm, and we use the formula as described there. Gm equals km minus kg. Put in the values. This gives us gm equals 4.02 meters minus 3.56 meters equals 0.46 meters. Next example, Km from the stability data is 5.22, Gm equals 0.78 meters. What is the Kg? We use the formula Kg equals Km minus Gm, and that gives us 5.22 minus 0.78 equals 4.44 meters. If GM is big, we say that we have a stiff vessel, which will roll quickly. Very quick movements. If GM is small, we say that we have a rank vessel, which gives us calm rolling movements. Slow movements back and forth. If the vessel is too stiff, it will be unpleasant to be on board with violent movements. Because of that, many vessels have rolling tanks, tanks that have as their purpose to reduce the GM, to reduce the stability of the vessel. A rolling tank is often a wide tank placed high up in the vessel, which is partially filled with water, and that reduces the GM, as we will see later. Summarized so far, the stability of a vessel depends on the hull shape, the shape stability, and the distribution of weight on board, the weight stability. The shape of the hull is given. What we can affect is the weight stability by the amount and the placement of weights on board. And by weights we mean cargo, equipment, fuel, etc., etc. Km is given and not dependent on how we place the weights on board. To make sure that the requirements to minimum GM are maintained, we have to make sure that the kg VCG doesn't get too big. Kg equals VCG equals vertical center of gravity. And how we find the kg is the next topic.